Okay, so this is the first technical session of the conference, folks. This is very nice. Fantastic keynote by Hari. Usually at this, if we are in person, there'll be great hallway conversation happening. Maybe we can carry that on in the various Slack channels. But in the meantime, it's time to begin the first technical session. And the first paper is towards formally verifying congestion control algorithms. It's a very exciting paper. As a PC member, I really enjoyed reading this paper. I worked a little bit both in congestion control and formal verification. And the way the authors put these two areas together is quite novel. The paper by itself is essentially a first step in this area. But I have really high hopes that the community will be inspired to do much more work in this area after reading this paper. Venkat Arun is going to present this paper. He's a fifth-year PhD student with Hari and Mohammed at MIT. He works in two areas, obviously in congestion control, where he seeks simplicity and formalism in their design. He is a co-designer of COPA, which is being used in production at Facebook. And he also works on making practical for communication systems to have thousands of radio antennas and explores new abilities for the scale that provides. Okay, so with that, shall we start the talk?
Hello, I'm Venkat Arun. Today, I'll talk about how to formally verify the behavior of congestion control. This is joint work with Meena, Ahmed, Mohammed, and Hari. Over the last 30 to 40 years that we've been working on this problem, people have proposed literally hundreds of different algorithms. And the typical design process goes like this. First, we come up with a new idea. We try it in the network that we were thinking of, and it works. We try it in a different network, and it breaks. Then we sit down, think for a while, come up with a fix, try it in the network where it broke before, and it works. Try it in the original network, and it breaks. And this cycle continues. I'm sure anybody who's worked on congestion control is painfully familiar with this process. So why is congestion control so hard? Well, there are many different types of network paths on the internet, and it is difficult for anybody to keep all of them in their head and ensure that their algorithm can handle all of them. Indeed, for every algorithm that we're aware of, there are network paths where it performs 10x away from optimum. And this is also our experience when Hari and I were developing COPA a few years ago, and I spent sleepless nights thinking of different ways in which COPA would fail. And this is called the congestion control anxiety, because we never really know whether an algorithm would break. And to fix this and to fix my sleep, we developed CCAC, which uses formal verification, and it systematically searches through an exponentially large set of network paths to either find a trace that breaks the given algorithm or prove that no such trace exists. And with this, CCAC introduces the notion of performance verification, where we use techniques developed for verifying the correctness of software to verify the performance of algorithms. And we believe that this is applicable beyond congestion control, and particularly good candidates are heuristics that have poor worst case behavior. We said that congestion control is hard because the internet can do a large set of things. What are some examples? First, this is the ideal view of the internet, where the sender and the receiver are connected by a single constant bitrate bottleneck link, and there's a fixed propagation delay. We can represent this graphically as shown here. The blue line is the arrival curve. This is the cumulative number of packets that have been sent. The slope of this curve is the rate at which packets are being sent. The red line is the service curve, and the gap between these two is the delay. And this is what most theoretical treatments of congestion control assume this internet looks like. However, the internet is more complicated than this. For instance, Wi-Fi routers create large bursts of acknowledgements because they don't send acknowledgements as and when they arrive. They wait for a large number of acknowledgements to arrive, and then they send them in a burst to improve wireless efficiency. But this can confuse congestion control because not all variations in delay and rate are due to congestion. We also have token bucket filters on the internet. So suppose there's an app that is idle for a while and then suddenly bursts packets. A token bucket filter will also burst a little bit before sending at a constant rate. And this is done to absorb small bursts and to improve application performance. But contrast this to what a constant bitrate link would have done. And congestion control algorithms can be confused into thinking that there's more bandwidth available than there really is. We can also just have regular errors, such as operating system scheduling errors, that make the service curve look a little bit jittery and random. These effects can combine too. We can have token bucket filters and OS scheduling errors. So on the left, we have the picture that shows what theoretical treatments assume the internet looks like. And on the right is what it can actually look like. And theoretical treatments also often ignore other complexities, such as packetization or the fact that losses are detected through duplicate acknowledgements and timeouts. CCAC is the first tool and method that can theoretically reason about phenomena that were previously accessible only through empirical methods. And crucially, it includes sub-RTT phenomena, which can often be the determining factor in a congestion control algorithm's performance. And therefore, theoretical analysis with CCAC is much more likely to correspond to reality. And an icing on the cake is that a lot of the proofs are automated, which has two benefits. First, of course, it removes the tedium from the human. And second, there are cases where computers are just better than humans. And we'll see two examples in this talk. We said that CCAC is a tool that searches through an exponentially large set of network behaviors. This set is specified by the network model. A network model essentially decides for each packet if and when it is going to be acknowledged. In our case, this is decided by an adversary. Now, this adversary requires two properties. First, it should be powerful enough that it can emulate all the network behaviors we discussed earlier and more. And this means that if an algorithm works in spite of this adversary, it's also going to work in any network that the adversary can emulate. And second, the adversary shouldn't be so powerful that it can emulate behaviors no algorithm can handle. And this is how roughly the model works. Consider the arrival curve as before. The service curve is what an ideal link rate would have done. In the model, we give the adversary some region where it can pick any service curve that it likes. The width of this region is the slack the adversary has to emulate different types of effects. There are also lots of other constraints. For instance, the service curve cannot be greater than the arrival curve. Therefore, the service curve has to be in this region. The other constraints ensure that the model has the two properties that we discussed earlier. Now, if the adversary wanted to emulate a token bucket filter plus some scheduler noise, it would pick a curve that looks like this. It can also pick any other curve in this region, and critically, CCAC does not specify any probability distribution over these curves. Therefore, it is non-deterministic and not random. Here's an overview of how CCAC works. Core to CCAC is an SMT solver. An SMT solver is like a SAT solver that takes a formula as input and tries to find an assignment to the variables of that formula that satisfy it. If no such assignment exists, it proves that this is the case. And in this formula, we encode our network model. And in doing so, we had to solve a few challenges that are detailed in the paper. And this forms the core of CCAC. To this, the user specifies formulas that describe the congestion control algorithm and their query. Their query encodes what sort of behavior they're looking for. For instance, they could be looking for cases of low utilization. And then CCAC outputs either an example of a trace that has the queried behavior, for instance, low utilization, or a proof that no such behavior exists. These proofs work over a finite amount of time and for fixed link rates. We can put a human in the loop to produce proofs that work over variable link rates and arbitrarily long time scales. In this case, CCAC does most of the proving, and the user is only left to do the interesting bits. We demonstrate this workflow using three algorithms: AIMD, BBR, and COPA. AIMD, of course, is the most classical algorithm, and conventional wisdom says that if the buffer is greater than a BDP, that means we have 100% utilization. And this is the sawtooth graph we're used to seeing. So consider a case where the buffer size equals the BDP. Packets will get lost when the congestion window exceeds the buffer size plus the BDP. And when this happens, the congestion window is halved. And as long as it stays beyond a BDP, we get 100% utilization. Now, if you have premature loss, then the congestion window can fall below the BDP. And this causes underutilization. And loss can happen, for instance, if the buffer overflows. And this can happen if the sender sends a large burst of packets that overwhelms the buffer. To understand when this happens, we ask the following query to CCAC. We gave it an example of a buffer size and the slack the adversary has, and we gave it this formula. This formula says, does there exist a T such that loss happened and the congestion window is small? We also need to specify the congestion control algorithm. So we do that also using logical formulas. So this formula says that if loss is detected, then the congestion window at time t should be half of the previous congestion window. The Boolean variable can decrease ensures that we do not have our congestion window twice in the same RTT. For the increase side, we have a similar formula. Before we discuss what CCAC found, here's a quick refresher. The sender maintains an estimate of the total number of bytes in flight, and this is equal to the total number of bytes sent minus the total number of bytes acknowledged minus the total number of bytes that the sender believes are lost. And the rule is, if the congestion window is greater than the in-flight, the sender sends packets. This means that it bursts packets if the in-flight suddenly drops below the congestion window. And this can happen if one of these two variables suddenly increases while the congestion window does not decrease. So let's look at ACT clocking. Now, the bytes ACT increases when ACTs arrive. And when ACTs arrive, packets are sent. So if the ACTs arrive smoothly, the packets are sent smoothly. If the ACTs arrive in a burst, packets are sent in a burst. And if this burst is large enough to overwhelm the buffer, we'll have premature loss and therefore underutilization. One might wonder that if the network has a buffer size of only 10 packets, how can it generate a burst of more than 10 acknowledgements? Well, maybe the burst is being generated by the Wi-Fi router on the reverse path. The fact that packet bursts can cause the sender to send a burst of packets is well understood. But what is much more surprising and CCAC uncovered is that if the sender detects a large number of losses, that can also cause it to burst. But this is surprising because the congestion window should also halve when this happens. But CCAC circumvents this mitigation. In the paper, we prove bounds on when this happens. The longer talk discusses an example. We also studied COPA, and we asked CCAC whether there are cases where it can get low utilization. And it answered yes, it can get arbitrarily low utilization. Then we asked CCAC, let's modify the model such that it can only emulate one jittery network elements, where previously the adversary could emulate multiple jittery network elements. And then we were able to prove using CCAC that COPA will always get greater than 50% utilization. So what happened? Well, COPA's key assumption is that if the sending rate is less than the link rate, then the queue will nearly empty at least once every RTT. But what CCAC told us, which we did not realize while we were designing COPA, is that even if this assumption holds for individual network components, it may not hold for a composition of these components. That is, while both of these components empty their queue, they may not empty it at the same time, leading to a persistent queue. We asked the same question for BBR, and CCAC again found that BBR can get arbitrarily low utilization. And what CCAC found is that BBR periodically tries to probe for bandwidth by creating a transient queue. But the network can absorb this transient queue and prevent BBR from ever realizing that more bandwidth is available. In conclusion, we'd like to say three things. First, CCAC provides the first mechanism to theoretically reason about various non-idealities on internet. And this includes sub-RTT phenomena. And this could enable the design of robust congestion control algorithms. And finally, CCAC introduces this notion of performance verification, which we believe could have wider applicability. Thank you.
Okay, so that was an excellent talk. And I realized that one major advantage of recorded talks is that they always end on time. You don't have to tell the authors to the speaker to speed up or any such thing. Okay, with that, we are ready to take some questions. I am watching the chat and I'm also watching the Slack channel. Here is maybe a question to start with. One of the concerns that I think many of us had when we read the paper in the PC is the exponential explosion of the state space, and you touched on that briefly. Do you have ideas on how you can manage that to make it so that this will become practical and usable in future?
So we do that in two ways. First, the SMT solver itself only searches for a finite amount of time. So even though it's exponential, the exponent is small enough that it's feasible. And then to extend to longer periods of time, we use mathematical induction. So the CCAC proves theorems over short periods of time, and then we stitch them together by hand to prove theorems over arbitrarily long time scales and also variable link rates. And this is elaborated both in the paper and in the longer talk. You're muted.
Thank you. Okay, so here is a question from Anna Brunstrom on Slack. She says, nice talk. How do you ensure that you have captured all relevant network behaviors when selecting the region for your network model?
Right. So the way we do is two ways. First, we prove that it can capture token bucket filters, and the network model also allows the adversary to emulate any arbitrary delays per packet as long as it does not reorder the packet. So this means it can automatically emulate scheduler errors, random MAC errors, packet aggregation, and so on. So we take a bunch of behaviors that we know on the internet, and we prove that the adversary can emulate all of those. And then we also prove that if it can emulate A and B, then it can also emulate a composition of these. And simultaneously, we also had to ensure that it doesn't emulate too many things, like things that no algorithm can handle. And we discuss those cases in the paper. Thank you for the question.
Awesome. We have time for only one other question, and this one comes from Aditya. So he says, thanks for the wonderful talk. What are the types of queries that CCAC can handle, and what are the queries it can't handle? I'd be interested in high-level condition control properties such as fairness, but the queries that you have shown in the paper are low-level corner cases. Is that the correct understanding? And maybe I guess the unsaid part of the question is, how would you handle questions about fairness and so forth?
Right. So the types of queries CCAC can handle are arbitrary logic formulas. So you can say things, of course, that the utilization is low or that the delay is too high. For AIMD, we also had a query that can loss happen when the congestion window is small. And we had a number of other like nuanced logical queries to prove the theorems. And as for fairness, we do not currently handle fairness. And I will say that's even though the tool can technically do it, it seems that fairness is much harder than we thought. So that is future work. Yeah. So, and the way to avoid corner cases is, so that's the goal of the tool, is to capture all of these corner cases that do occur on the internet. And for everything that CCAC output, it looks like there are paths on the internet that have that behavior that CCAC said they were. And that's because the model was designed to ensure that. Yeah. So to summarize, we can handle logical formulas as queries, and we have not done fairnesses yet. That's future work.
Okay. So I think that's all the time we have, unfortunately. So Venkat, if you don't mind, if you hang out on the SIGCOMM'21, that's the channel. If people have more questions, they can ask it there. And with that, let's move on to the second talk. The second talk is called Aquila, a practical verification system for production scale programmable data planes. Typically when you see verification papers, they're focused largely on control plane behaviors. This is one of the first papers that I've seen, at least, on data plane verification. This is a actual deployed system in Alibaba. The paper will be presented by, and I'm going to butcher these names now, unfortunately, Bingchuan Tian and Enan Jai. They're both engineers and researchers at the network research team of Alibaba Group, and their research focuses on building reliable and secure networking systems for Alibaba's global network.
Hello everyone, I'm Bingchuan Tian from Alibaba, and I just received my PhD degree in Nanjing University. Today I'm going to present Aquila, a practically usable verification system for production-scale programmable data planes. This is a joint work during my internship at Alibaba with my colleagues from Harvard University. As a prominent online service provider, Alibaba operates a global network infrastructure serving over 1 billion customers. As services today constantly evolving in size, it's becoming increasingly difficult for edge networks to handle the ever-growing traffic due to resource constraints. This promoted us to offload a group of network functions from servers to save CPU resources and get better performance. Recent advances in programmable networks have enabled us to implement network functions using P4 language. It gives us a cost-effective solution to greatly improve the performance of our edge networks in terms of both functionality and efficiency, as well as flexibility. Given these advantages, we have widely deployed programmable switches in our edge networks. With the increasing diversity of our services, the data plan programs are greatly increasing in complexity. Each program may consist of thousands of lines of P4 code and multiple pipelines, and each pipeline holds a number of network functions, such as NET, load balancer, and DDoS defense. The network functions across different pipelines are tangled with many packet paths, resulting in complex function chains within the single switch. Therefore, it's a great challenge for developers to ensure the correctness of data plan programs. To prevent any possible data plan bugs, we need a practically usable verification system to rigorously verify the correctness of data plan programs. To make the verification system practically usable, a simple and powerful language is required to help developers write their intent in an easy way. The verifier should be able to verify production-scale data plan programs and give results within a tolerable time. When the verification task fails, the verifier should try to localize the bug, instead of just printing a counterexample on the trace. And last, the verifier should be confident to its verification result, and try to avoid false positives and false negatives. The above 4 points correspond to our 4 challenges. The first challenge is about the intent complexity. It's not easy to describe some intent accurately in a simple way. For example, see this intent. For each TCP packet, we shouldn't change its TCP header. It's very natural for us to understand it. But from a verifier's perspective, what's the definition of the TCP packet? Is a packet with TCP header a TCP packet? Or a specific header order is required? Here, of course, the second packet is not what we want, but it's not easy to tell this point to the verifier. If we follow existing work, we will have to write a lot of lines to express this intent. It's very complex and also error-prone. It would be much better if we can express it in one line. The second challenge is about the scalability. Our production programs are composed of a layer 3 switch and a lot of network functions. It's not easy to verify such a big program efficiently. In addition, our production programs are mainly written by P416. Unlike P414, P416's match action units are divided into 2 logical pipelines. Each pipeline has its own parser and deparser. Unfortunately, it's exactly the parser and deparser that contributes the major complexity to verification. Existing works are not scalable to our production P416 programs. The next challenge is about bug localization. When the verification task fails, existing work only print a counterexample and a bug trace. However, it's not enough. In our production programs, the bug trace contains over 100 steps, and it's still very hard for developers to localize the bug. The last challenge is about the reliability of the verifier itself. A verifier can also have bugs, which may mask the program's bug. So a validation mechanism is required to make the verifier more reliable. But no existing P4 verification system can do self-validation. To solve all above challenges, we built a production-scale data plan verification system, Aquila. Based on our experience in developing P4 program, we designed a simple and powerful intent language to help developers describe the desired property. Next, we proposed a set of encoding algorithms to translate P4 programs into a guarded command language and solved the scalability problem. Then, we reused the verifier to build a bug localization algorithm by analyzing the causality of the bug. And last, we use a cross-checking algorithm to validate the correctness of the verifier. Now, I will introduce the first part, the intent language. The key insights of intent language are summarized from our experience. For example, we noticed that the most intent can be placed before a pipeline or after a pipeline, but seldom inside the pipeline. This gives us a chance to represent the intent as a single independent file, instead of adding annotations in P4 code. With our intent language, developers can easily describe the properties about parsers, match action units, and program architecture. Next, I will introduce how to make the data plan verifier fast and scalable. We use Dextra's classic method to verify a program, so we make no claim on the novelty of verification technology. Instead, our contribution is how to encode a P4 program to another program that can be efficiently verified. To achieve this, we need to solve a lot of problems. In this talk, I will only introduce the state explosion problem of the packet parsers. Look here, here is a packet parser, and it's also a state machine. In each state, the parser extracts corresponding packet header and then transits to another state according to the field of the header it parsed. Look at this transition. It's not a typical branch structure because it has two parallel exits. That means we can't express it with the if statements. A straightforward way is to expand the state machine into the tree, so that we can easily express the tree with the if statements, and then it's trivial to verify the program. However, we can see that at the bottom of the tree, two states are duplicated. It's okay for small programs, but not acceptable for large programs, because the tree can be very deep. In the worst case, there can be over 1,000 duplicates. Verifying such a malformed program requires a lot of memory and several days. To solve this problem, we proposed sequential encoding to reshape the state machine. Let's assume the parser is acyclic, so that each state can be visited at most once. In addition, for any two states, they are either mutually exclusive or have a fixed order of execution. That means the acyclic parser can be regarded as a sequence of states. Each state can be visited once or not visited, depending on previous states in the sequence. For example, whether to visit the TCP state depends on the protocol number from IPv4 or IPv6 state. Whether to visit the IPv4 state further depends on the Ethernet type from Ethernet state. Here is an example of sequential encoding. We use the following 4 steps to translate a state machine into the simple verifiable program without any code duplication. There are some details remained. For example, how to encode external functions, and how to handle the parser loops. In this talk, I will skip these details. You may find them in our paper. Now, let's see how Aquila performs. We choose invalid header access as benchmark to evaluate Aquila's verifier, and record the time to find the first bug and find all bugs. From the results, we can see that without Aquila's encoding algorithm, it's almost impossible to verify multi-pipeline programs with complex parsers. Finally, I will use a real example to show how Aquila is used in Alibaba's P4 verification. Here are the pipelines of production-scale data plan programs. Layer 3 functions are implemented in switch ingress and switch egress, while custom functions such as load balancer are implemented in LB ingress and LB egress. One day, our developers need to decapsulate VXLAN packets in LB egress and then route the decapsulated packets. But routing tables are placed in switch ingress. There is no hardware resource to place another routing table in LB ingress. To solve this problem, our developers decided to swap the switch ingress with LB ingress. This changes the dependency between the two pipelines. For example, the net function is originally placed in LB ingress, while the echo function is placed in switch ingress. After the swapping, the echo table will match the netted address instead of the original address. We use Aquila to verify whether the semantics of each function are equivalent before and after the swapping, which proves that Aquila is practically usable in verifying production-scale data plan programs. In conclusion, Aquila is the first practically usable verification system for production-scale programmable data plans. It provides a high-level specification language, a fast and scalable verifier, a bug localizer, and self-correctness guarantee. Aquila has been used in Alibaba for more than 1 year and found several bugs in our data plan programs. This is the end of my talk. Thanks for listening.
Okay, so that was wonderful. And please ask your questions on the Slack channel, which I can relay, or here in chat, and I'll get this kicked off. I have a question that is actually not necessarily about verification. So in Microsoft, for example, when we have deployed verification systems at scale, one of the constant challenges has been how to structure the UI or the interface around it so that our developers can use it, or so that our network engineers can use it, right? We don't have data plane verification. We have mostly done control plane verification work. And we typically operate with GitHub repositories and being part of CI/CD pipeline when config changes are checked in and so forth. I'm curious, how have you guys structured the interface to the developers? What happens? So when somebody checks in a P4 configlet, there's a CI/CD pipeline that your code kicks off. Just curious. And how is the feedback provided? Because sometimes actually reading the feedback itself is a challenge. We have repeatedly found that you have to provide feedback in a very concise manner. Otherwise, people simply ignore it or get even more confused.
So yeah, this is a this is interesting question. Actually, we try to design our interface as the the graphics way, for the operators and programmers to express their specification or the intent. Typically, we just ask them to draw some pictures there, and we provided some icons there, and they can just draw them there. But in most of the time, we may not be able to design such picture way. So in that case, we just provide an IDE way, and they can just write a program like what they write the C program or Java program. But I guess this should be improved in any company, also including the Alibaba, because we just provide some pure text edit tool. They just program there, and I guess we will in the future absolutely add more. I think tool list and to for example color the keyword or programs and to give some feedback there. But unfortunately, we now mainly just have the normal idea for them to program. But typically for the very specific case, we just provide the picture way. They just draw something. But I guess for the data plane programming and data plane verification part, that's just the normal programming method to write the program or write the specification. This is what I can contribute to your question. Yeah, but for the control plane verification, like what we presented last year, yeah, they can draw some pictures there and put the intent there. Yeah, but that's not for the programmable P4 verification part.
Okay, wonderful. So we are at time, so I'm gonna let's take more questions on Slack. So if you guys join the SIGCOMM'-TS1 channel, that's where we will do more questions. And with that, let's go on to the next talk. And this talk is called Snowcap, Synthesizing Configuration Updates. This is a slightly different problem compared to the standard verification problems. So most verification papers focus on either the current set of router configurations or the goal state. But the key question to ask when running a very large network is how do you safely go from present state to goal state, right? And there are typically many ways to do this. And even if you have verified both the starting state and the goal state to be safe, you want to make sure that as you go from current state to goal state, because a change cannot be instantaneous, you have to update many thousands of routers sometimes. You do not violate certain constraints that you have in your mind. This is typically done manually, and this paper provides an attempt to synthesize the steps. I enjoyed reading this paper. This is a very real problem. And I'm looking forward to listening what the authors have to say. The paper will be presented by Tibor Schneider, who's a first-year PhD student at the Network Systems Group at ETH Zurich, advised by Laurent, and his research aims at improving methods for verification and synthesis of network configuration. So let's go.
As network operators, we configure our networks from scratch only once. Changes after that are reconfigurations, and these happen very often. Business relationships between neighboring networks change on a daily basis, which require us to change the routing policies. These reconfigurations only modify a single router, but they can happen up to 20 times per day on average. Networks may face new requirements every couple of weeks, which poses new challenges for traffic engineering. Such reconfigurations involve multiple routers in the network. Now finally, we sometimes completely redesign our networking infrastructure to adapt it to new network paradigms. For this, we must change the configuration of every single router in the network. These medium to large-scale reconfigurations can be extremely disruptive. A study from Alibaba has revealed that more than half of their network incidents are due to changing the configuration. So let's look at a simple example to highlight these issues. Here we have a small network with one firewall and one external peer. Our goal is that the traffic from Rx to the external peer will always traverse the firewall. We can achieve our objective by choosing the forwarding state something like this. And this forwarding state can be implemented using OSPF and these set of link weights. Now let's pick this as our initial configuration. But observe that the link between R2 and the external peer is a single point of failure. And we now want to fix this by adding redundancy. So we add an additional physical link and a BGP peering session between R1 and the external peer. But if we would simply do that, then Rx would bypass the firewall, because it can now reach R1 with a cost of 10 instead of R2 with a cost of 18. Therefore, we also increase two link weights, such that the path from Rx to the external peer is not affected. Let's pick this as our final configuration, and to migrate, we need to make 3 changes on 3 different routers over 2 different protocols. So let's just start reconfiguring the network. What can go wrong? If we first add the session, then, as we already discussed, Rx will bypass the firewall, which is not good. So we first need to increase the link weight between Rx and R1. But if we do that and then add the external session, then we will have an unnecessary traffic shift at the firewall. So in this case, the best way to perform this migration is to first change both link weights and then add the external session. And this can be very easy to see for this small example, but what if the migration becomes bigger? So for bigger migrations, we try to follow best practices. But this is not enough, as we show in our experiment. We simulate the scenario of migrating from an IBGP full mesh to a route reflector topology, which is a very common migration scenario that most smaller networks will perform when growing in size and complexity. We use around 80 different topologies from Topology Zoo and prepare such a migration for each of them. Then, we pick many random orderings of routers to reconfigure and count in how many of these orderings some flows will end up in transient black holes or forwarding loops. Now, as a baseline, we select a completely random ordering of routers. In 70% of the migration scenarios, more than half of these random orderings will break reachability. Now, according to the literature, best practice is to reconfigure all route reflectors before the others. So following this best practice yields a slight improvement. But nevertheless, in a quarter of the scenarios, there is a large chance to break reachability. As we have seen, these best practices cannot give us any safety guarantees. But in addition to that, these practices are prepared for a specific protocol and migration scenario, so they cannot be applied universally. This is clearly an important problem, and we're not the first ones to look at it. Existing systems can be distinguished into 2 different categories. Offline systems run the initial and the final configuration at the same time. Then, they wait until the final one has converged, while still forwarding packets according to the old configuration. Finally, these systems activate the new configuration on one router after the other in an ordering that preserves the objective. While offline systems can guarantee safety for any protocols and migration scenarios, they introduce additional memory overhead as the control plane is essentially duplicated, which makes them less practical. On the other hand, online systems directly change the configuration of the live network. They synthesize multiple small changes to the configuration that can be applied to the network one by one. While not adding additional overhead, they only support a limited set of scenarios and protocols, mainly link state IGP. This makes them less practical, as most of today's network are running a combination of BGP and IGP. So we present Snowcap, a system that automatically and safely performs reconfigurations on the live network, but is general with respect to protocols and reconfiguration scenarios. Here you can see a high-level overview of the system. As an input, it takes both the initial and the final configuration, which are both assumed to be verified and correct. Then it computes the difference between those two configurations to get a set of commands. These commands are necessary to perform the migration. Next, the operator specifies a set of specifications, which are properties that must be satisfied during the migration. We call those the hard specification. As in the example from before, the hard specification would be that Rx must always traverse the firewall to reach the external peer. The specification language of Snowcap is extremely flexible. It is built by combining a set of basic policies that are reachability, isolation, redundancy, and waypointing, which is a regular expression that matches on a path of a flow. But typically, operators change their configuration to adapt their network to a new specification, so the specification is changing over time and not constant. Therefore, these policies can not only be combined with Boolean logic, but also with linear temporal logic, which adds a time dimension to the specification language. Operators can now precisely express how the migration should happen. In addition, operators can specify a soft specification, which is a cost function that compares different migration sequences. Because not all orderings that satisfy the specification are equally good. For example, we might want to reduce the number of traffic shifts, because these might have a negative impact on the performance of the network. Based on the initial and final configuration, the hard specification and the cost function, Snowcap will find an ordering of these commands that will satisfy the hard specification while minimizing the cost function. Snowcap will then apply these commands one by one to the network, letting the network converge in between. This way, Snowcap can safely perform the network migration. The main challenge of Snowcap is how to effectively navigate this large search space. Because of course we have a factorial growth of the number of possible command orderings with increasing number of commands. But what makes it even worse is that most of these command orderings are actually invalid. Simply picking a random ordering until we have found a valid one by chance doesn't scale. So how does Snowcap do it? In the following, I want to explain how Snowcap effectively navigates this large search space. In the first part, I explain how the basic exploration mechanism of Snowcap works, and then I will show you how we can extend this mechanism to effectively isolate problems. For the basic exploration algorithm, Snowcap generates a tree of different orderings. In this tree, every node represents an ordering and every edge represents a command that can be applied to that ordering. Snowcap explores this tree in a depth-first search traversal. At every step, Snowcap tries all the remaining commands and picks the one that is valid and has the lowest cost. This results in a greedy optimization, and hence we do not guarantee that we find the global minimum. But later I will show you that this approximation is still very good. So this works extremely well in most cases. But what if we get stuck? It is possible that none of the remaining commands can be applied anymore. And this is usually due to a problem earlier in the sequence. Now let's take the example here on the left. And let's assume that command R must be applied after both V and W. Now the DFS algorithm would simply backtrack and explore all the possible options until finally resolving the issue. However, if the problem is earlier in the sequence, this backtracking can take a very long time. Instead, Snowcap actively finds these dependencies. On the higher level, Snowcap is using a counter-example guided search strategy. In the exploration phase, if it gets stuck, it takes one of these failing sequences as a counterexample. Then it tries to isolate the dependency inside of this counterexample. In a divide and conquer manner, Snowcap tries to solve the isolated dependency to find a valid ordering for just this reduced problem. Snowcap then switches back to the DFS exploration, but the learned dependency will now be treated as a constraint that it must appear in this order as we have learned it. With this, Snowcap can solve difficult dependencies in isolation and thus speed up the search significantly. So how does Snowcap scale, and how effective is it at minimizing the cost? To evaluate this, we look at around 80 different topologies from Topology Zoo, and these range from around 10 routers to up to 82 routers per network. We used common migration scenarios described in the book Network Mergers and Migrations by Junos. For each scenario, we choose random link weights and a random IBGP topology. And as a side note, Snowcap is only executed on a single thread. So let's go back to the case study from the beginning of this presentation. As a quick reminder, we have simulated a migration from an IBGP full mesh to a route reflector topology. And we have shown that even when applying best practices, in about a quarter of the scenarios, there is a large chance that the migration will cause transient black holes or forwarding loops. Now, using Snowcap, every single migration resulted in no transient anomalies at all. It takes Snowcap around 12 seconds to find a solution for the biggest problem. And this problem contains more than 3,000 reconfiguration commands. And on average, it takes Snowcap less than 1/10 of a second to find a solution. So let's now look at how effective Snowcap is at minimizing the cost. Snowcap only performs a greedy optimization, so it is not guaranteed to find the global minimum. In the following, we will look at two different scenarios and try to minimize the number of traffic shifts during the migration. In the first experiment, we perform a network acquisition. Here, we add several physical links and IBGP sessions between the two networks, and we rescale the link weights of one network to fit the other. On the x-axis, we show the different scenarios and topologies, and on the y-axis, we compare the number of traffic shifts. This red line is the number of traffic shifts when performing the migration in a random order without actively minimizing the cost. In comparison, Snowcap typically is able to reduce the number of traffic shifts by about half. In the second scenario, we do the same thing, but for doubling all the link weights. Here, Snowcap performs even better, usually finding an order without any traffic shifts, while the random strategy does not. So to recap, Snowcap is a system that is able to safely and automatically perform network-wide configuration updates. It does work for arbitrary protocols and arbitrary scenarios, and it doesn't pose any additional overhead to the networking infrastructure. If there exists a valid solution, Snowcap will find it. Snowcap is open source, and you can find the source code and the documentation on the project website. So this concludes our presentation. If you have any questions, I will be happy to tell you more about the system. But otherwise, you can find all the important information in our paper or on our project website.
Okay, so are there any questions? I am watching the Slack channel, and I believe that Bena's had a question early on, and she is wondering, Benas, this is a question for this paper, correct? Why these problems can't be detected by theory built by Tim Griffin, etc. There was some earlier work by Alex Gurney on how you can use theoretical properties along verifiers to ensure correctness. Snowcap seems like it could at least be improved using this prior work. And I believe that Tibor has already answered that. But Tibor, do you want to take this question here? I think Tibor, you're mute. Tibor, you're muted. Sorry, you're still muted.
Now, does it now work?
Yes, much better. Yes.
Sorry. So I don't know if I'm referring to the correct paper, but if I'm understanding it correctly, these papers are looking at how BGP converges itself, and not on how you can move from how you can move from one configuration to another, while ensuring that in between the configuration is correct all the time.
Okay.
So I think they are not solving the exact same problem, but yes, Snowcap can be improved by using these prior works.
Okay. We have time for one more question, and this question is from Neha Raje from Microsoft, and she says, "Great talk. How does this take into factor temporal dependencies in very large networks? Sometimes convergence takes time. How do you determine command ordering? I'm assuming that we base it on a stable network, but how can it be enforced or determined in an actual network?"
So yes, we look at it on a stable network. So you mean that different inputs are coming in and the network changes over time, probably. I think that you can express these temporal properties as in the specification, and then you might be able to use Snowcap as it is, because it's if not, then I might have to think about that.
So let me expand on Neha's question a little bit, because I know where she's coming from. We work in the same team. So suppose you apply a command. Suppose Snowcap has given a set of steps to go from A to B, right? And you are on step 1, and you now need to go to step 2, right? Before you go to step 2, your assumption is that step 1 has been completely applied and has been applied correctly, right?
Yes.
What if that doesn't turn out to be true? Or what is the amount of time you need to wait? What is the verification step that step 1 is completely applied and therefore it is safe to apply step 2? Because you could, in theory, end up in a situation where step 1 is either partially applied or has not yet finished taking hold at all the routers. And therefore, if you apply step 2, you could potentially go wrong. So what's the barrier synchronization, if you will, right? Like how do you know that it's safe to go to step 2?
So what we do is in the runtime, we check periodically if some changes are still happening to the forwarding state or to some tables in the routers. And if there are, then we wait longer. And if there are not, if the state of the routers remains constant, then we can perform the next update. It doesn't need to be very fast, this step, because we already know that the state in between is correct. So it is okay if we wait a bit longer. Yeah.
Okay. I think we are at time. We're actually a minute over. So I'll let you answer the rest of the questions on Slack. And thank you very much. And let's go to the next paper. The next paper is synthesizing safe and efficient kernel extensions. And this paper is about essentially eBPF, which is rapidly emerging or has emerged as a practical and scalable way to do Linux kernel packet processing extensions. And this talk is about K2, a new compiler that optimizes the BPF programs, providing formal correctness and safety guarantees. The paper will be presented by Qingwen Shi. She's a rising third-year PhD student at Rutgers, advised by Professor Srinivas Narayan. And her research interests are broadly in programmable networks. And she's currently working on designing compilers for optimizing packet processing. So with that, let's go to the talk.
Hello, everyone. I'm Chongwen. The focus of this talk is to optimize packet processing programs written in the Berkeley Packet Filters BPF framework. BPF is an emerging technology to do customized and high-performance packet processing. It's been widely used in industry. Facebook uses BPF for high-performance load balancing. Google uses BPF in its Kubernetes clusters. Recently, a few companies came together to launch the BPF Foundation, showing their long-term investment in this technology. So what is BPF? Modern BPF is a general kernel extension mechanism. It's extended from classic BPF, which was used to write packet filters. In this talk, when we say BPF, we mean the extended version. Users can write and attach BPF programs to different points within the kernel to process packets. BPF programs can be loaded in the system core, socket and TCP/IP layers, traffic control, the network device driver, smart NIC, and so on. Within the kernel, BPF programs runs in a virtual machine with basic instruction set. The virtual machine has 11 registers and a stack. BPF programs may use key value maps that may be shared with other BPF programs and with other user space processes. BPF programs may also call help functions to invoke specific functionality, which is baked into kernel's code. This is the workflow of a BPF developer. Suppose our target is to write and execute a BPF program in the network device driver. First, we can write a BPF program in C and use client to compile it into BPF bytecode. Then use a system call to load the bytecode. The bytecode will be checked by the kernel checker, a component in the kernel that ensures the safety of bytecode. BPF enables unprivileged user code to run directly in the kernel context. Hence, The checker is crucial to ensure that malicious or buggy user code cannot crash the operating system or leak any privileged data. The checker proves safety by doing a static analysis over the bytecode. If the bytecode is accepted by the checker, a JIT compiler within the operating system will convert it into native machine code. Finally, the program can be executed within the network device driver. But it's not easy to develop high-quality BPF programs. There are two reasons. The first problem is size. Because the kernel checker must verify a program safety quickly, the kernel bounds the number of instructions it examines for each program. On modern kernels, the limit is 1 million, including examining the same instructions across different code paths. In practice, even a program with a few thousand instructions may be rejected. To get such programs accepted, a developer must disable some features or refactor the code. The second problem is about performance. We'd like BPF programs to have excellent performance, because at high rates, even small improvements can lead to significant CPU cost savings. One approach is to have developers manually optimize BPF bytecode, but it requires developers to be familiar with BPF. If the program is long, this is painstaking work. Another approach is to use compiler support for optimization. However, this is lacking today. For the benchmarks in our experiments, higher optimization flag 03 produces the same code as 02. This isn't because 03 is already amazing. We have identified several optimizations over 02 code. This is the problem statement of our paper. Can we automatically produce compact and more performant programs? The key challenge is the tension between performance and safety. The kernel checker is stricter than needed. The checker's static analysis has many heuristics baked in to reduce the number of cases it needs to consider, and hence reduce the time to check the program safety. So a program that's in fact safe may be spuriously regarded as unsafe by the checker. Here's an example. This program stores 2 bytes on the stack. However, it's rejected, since according to the checker, stack access should be aligned to the size of access. If we modify the store address, it will be accepted. The tension with safety makes it challenging to design compilers to optimize code. Traditional compilers match patterns over small portion of code and rewrite them into efficient code. In this example, the first instruction sets memory as 0. The second one sets the next memory as 0. We can design a pattern to optimize these 2 writes into 1 write. However, such optimizations are frequently incompatible with the checker's constraints. Recalling the stack access alignment example we showed before, this optimization will be rejected if the stack access is not aligned to 2. Every potential optimization must also consider safety, since such safety constraints apply to many optimizations. Being conservatively safe precludes many optimizations, while optimizing aggressively risks program being unsafe and hence rejected. We call this the phase ordering problem of BPF compilation. Developing better optimizing compilers requires considering both optimization rules and safety constraints. We design and implement K2, a BPF optimizing compiler, which takes client-compiled BPF bytecode as input, produces drop-in optimized bytecode. Over a set of realistic benchmarks, K2 improved code size, packet processing latency, and throughput relative to the best client-compiled programs. K2 leverages stochastic program synthesis to optimize programs. K2 provides formal correctness and safety guarantees. We do this by encoding the BPF instruction set in first-order logic. K2 formally checks equivalence between BPF programs and safety predicts over the program using logic. We introduce several domain-specific techniques that reduce equivalence checking time by 6 orders of magnitude compared to naive formalization. Our formalization can encode practical BPF programs It handles arithmetic and logic instructions, memory aliasing, control flow BPF maps, and helper functions. You can see the details in our paper. Next, I'll unpack why and how K2 uses stochastic program synthesis. Program synthesis is a search procedure that automatically generates a program satisfying a specification. Our specification is complex, combining correctness, safety, and high performance. By considering them together in the search, we address the phrase ordering problem. Stochastic synthesis is a randomized algorithm to explore the space of programs based on MC-MC method. The search is guided by a general cost function evaluated over programs. This is not the state-of-the-art approach to synthesis. However, compared to other approaches we considered, it's fast and generalizes easily to BPF optimization. Stochastic search can handle complex costs with complex constraints. At a high level, K2 takes a BPF program as input and produces optimized BPF program as output. The given input program is the first program for K2's stochastic search loop. At each iteration, K2 performs a small random modification to the current program to generate a new program called a proposal. K2 computes the cost of the proposal. The cost is a combination of correctness, safety, and performance. If the proposal's cost is at most slightly larger than the current program, it will be accepted. The proposal becomes the next program used as the base for modification within the search loop. Whenever the proposal is accepted and its safe equivalent, it will be added into a program database. After a configurable number of maximum iteration, K2 will rank all the programs in the database and emit top K programs according to performance. These programs are all correct, safe, and have the best estimated performance. K2 makes several domain-specific contributions. We propose several program modifications to generate proposals, reducing the search time to find better programs. As part of cost computation, we introduce techniques to check equivalence of programs with pointer aliasing, control flow, BPF maps. K2 introduces several optimizations to check equivalence faster. Notably, we propose methods to check a small window of the program while still being aware of the program's context within the program. K2 is the first work that proposes and leverages safety counterexamples, a fast method to prune unsafe programs using test cases. So, how well does K2 work? We evaluate K2 in terms of two performance goals: program instruction count reduction and program performance improvement in terms of latency and throughput. We use K2 to reduce the number of instructions in 19 benchmarks. Here's a part of results. We compare K2's results with the best client version. The comparison ranges from 6 to 26%. The average compiling time is about 22 minutes. This table shows the throughput improvement of 6 benchmarks running in the device driver. Gains range from 0 to 4.75%. We measured average round-trip latency for 4 benchmarks running in the device driver. The reduction is from 1 to 55%. Why does this work? To understand the evaluation numbers, we cataloged optimizations that K2 derived automatically. You can find a detailed list in the paper. Here are 2 optimization examples found by K2. The first example combined 2 writes into 1 write, reducing 2 instructions. The second optimization comprises the program leveraging the context of the window within the program. K2 used the value of R3 written in a prior instruction to optimize the window. In summary, we presented K2, an optimizing compiler that produces programs with reduced size and higher performance. K2 contributes several domain-specific techniques for the synthesis and verification of BPF programs. Looking forward, we believe that synthesis is a viable approach to optimize packet processing programs. Thanks for your listening.
Okay. So are there any questions? Let me check on the Slack channel here. No, I think we don't have any questions on Slack. So let me kick this off. I think my question is very simple. I wish we could throw the slides back on. In one of the slides, you said that the optimizations got 4% gain, and then you said that the round trip times had 55% gain. So I'm a little bit confused about how to reconcile those two. Maybe I saw something wrong. So.
Oh yeah. So so when we do the experiment, we use two machine. The first machine sends some package to the device under test, and we attach a XBP program, which is a BPF program attached in the device under test machine's network device driver, and then this BPF program will forward back the packets to the machine that is sending the packets. And that's how we measure the latency and the throughput. And actually, I would like to see that for the latency, actually, it's not the so it's the latency in at different packet sending rates. Like when the packet sending rate is super low, lower than the throughput of client and K2, and also the sending, and when the sending rate is at the lower level of client or K2, or higher level of client K2, or at the saturating speed. So this loop, so that's how we measure the latency.
Okay. So I'll read a question from Slack from Ankit Gaur. Would K2's optimizations be applicable to P4 programs as well?
Sorry, could you?
Will the same ideas work for optimizing P4 programs? That's what Ankit is asking.
Go ahead. Sorry.
Oh, sorry. So for P4 programs, in our work, we proposed a general framework to optimize programs with the constraints of safety, performance, and correctness. So for P4, we can encode, for P4 program, we can encode its safety constraints and as a way to estimate whether P4 programs running time is good or not, and also the correctness. That is, we need to ensure the two P4 programs, the optimized P4 programs is semantically equivalent to the input P4 program. So here we need to encode the correctness constraint for P4 programs. So these are three parts that we need to modify to support optimize P4 programs.
Okay, wonderful. So I think we need to end this session because we need time for sponsor videos here. There are still questions on the Slack channel. So SIGCOMM'-TS1, please continue the discussion over there. So thank you. And that's the end of session 1.